Okay, so what we'll be doing, so let's try to understand the gauge invariance. Although I have already done it in the previous semester, how the concept of gauge field arises. So let me do it again. So let's take, okay, so let's think of the scalar field. Okay, so I'm having the scalar. Okay, so what I'm trying to do, so we'll be actually gauging a symmetry here. In a sense, let's say if I'm having a global symmetry, I want to make that symmetry local. And what are the consequences of making a given symmetry to be local? What does that mean? Let's say if I'm having a symmetry of a given Lagrangian, okay, a global symmetry, or simply a phase, simply an invariance under a phase transformation. Now let's say that phase depends locally on the coordinates. What will happen? Okay, so let's try to understand that. Okay, so let me take the case of the scalar field. Okay, so let's take the scalar field first and try to understand. So this is the complex scalar field. Okay, so free field, I am just taking the free field without any kind of interaction. Now if I make a transformation from phi to phi prime is equal to e raised to minus I q some theta, where theta is a parameter, okay, of the rotation. Q will simply q will be called as a charge. Okay, q is a charge carried by the particle or carried by the field. Okay, so we can figure out this q is as a rotation of the charge. So this is simply a phase rotation. Clear? So now if I take this very phase rotation, now let's check whether the Lagrangian is invariant or not. Okay, so here theta is independent of coordinates. So I will call this as a global phase rotation, which you already know, global phase or a global U1. Okay, because it's a unitary group. Okay. So now let's look at whether this Lagrangian remains invariant. And if I take phi dagger, so you will be having e raised to I q theta, that will come out. From here it will be e raised to minus I q theta, that will come out. They will cancel, is it? They will yield a 1. This will also yield a 1. Clear? So it implies therefore the Lagrangian which under this very transformation, that is same. Okay. Similarly, if I take now the Dirac field. Okay. So let me take the Dirac field. So what is the Lagrangian? In the simplest of way, you are having psi bar I partial slash minus m psi. Clear? This is the free Dirac field, and let's check if my psi also goes in the same way. This psi prime is equal to e raised to minus I q theta psi. Okay? So I should put an argument the x here because it's a dependent, so that field it is clear fields have the space-time dependence and theta does not have. Okay. Now let's look here. You are having psi bar. Psi bar is essentially psi dagger. Clear? Is that true? So it will make it plus e raised to plus I, and you are having e raised to minus I theta here. So they will cancel out. Clear? So that means, so which implies this L will go as some L prime that will be same as L. So in other words, under a global phase rotation, it is simply a rotation. You rotate the entire field and you will see our Lagrangian remains same. Got it? Okay, so this is, this is the symmetry possessed by these free fields. Okay, you can calculate the Noether current corresponding to this thing. Since you are, this is actually a continuous symmetry yields a conservation law by Noether theorem. you can calculate actually the conservation. Okay, so let's say in case of this thing, so this I will not do in detail. So you will be having a conserved current. So that is J mu is equal to some Q psi bar gamma mu psi. Okay, so this is the conserved current in case of the Dirac field. Okay, so that's all about this global phase rotation. Now what I will do, so let me make okay, so let me make this theta dependent on coordinates x. Clear? Got it? So here it does not depend on the coordinate. Now I will fix this theta in such a way that it depends on what? A coordinate. Okay, or make it coordinate dependent. Now what will happen? Okay, so we will be interested in the Dirac field. Okay, so let's make this theta coordinate dependent. So that is, it will be a theta is simply a function of x. Okay, so what is our phase rotation now? Okay, now look here. Since this, okay, so let's take now the same transformation. This psi of x goes to some psi prime x prime. Okay, some psi prime x. Okay, is equal to e raised to minus I q theta x and psi. Now look here. Okay, so since this depends on the the coordinate, it means what? It's a local transformation because it will depend upon a coordinate at a for a given point. Samushima, for each different point, this theta will be different. Clear? Because it has a coordinate dependence. Previously, it was same for all points in your space time. Clear? Samushima, in that sense, we call this as a local phase transformation. So we have now gone from a global phase transformation to the local phase transformation, or we call it sometimes local U1, because it's a U1 group still. It's a unitary group. Now let's check whether that Lagrangian is invariant under this transformation or not. Okay, so therefore I will write this Lagrangian. Okay, so my Lagrangian goes to sum as L prime as some psi bar prime. So you are having I gamma mu partial mu psi prime minus m psi prime psi. So this is our Lagrangian. Now what this psi bar prime is? So it will be simply e raised for I q theta of x some psi bar. So I gamma mu partial mu. So now you have to take the derivative. So e raised for minus I q theta of x psi minus m. So it will be psi bar will be something e raised for I q theta of x. Then you are having e raised for minus I q theta of x coming from psi. So you are having psi bar psi. Okay, so now let's take the derivative here. Okay, so what you get? Just tell me. So which implies your L prime, that's equal to. Okay, so the first term, so you take the derivative on this thing, keep this out. So then this exponential and this exponential will make 1. So it will be simply psi bar I gamma mu partial mu psi. Then the another term plus you are having this psi bar I gamma mu. The differentiation, what is the differentiation of this very factor? Minus I q, so it will be partial mu theta of x. Okay, then you are having the exponential outside. Okay, this will make 1 with this thing. And you are having psi minus m psi bar psi. So what you are having, so this term is our original Lagrangian, psi bar I partial slash minus m psi. Then you are having minus and minus is plus. So q, so let's take this partial mu theta out because it's a number. Okay, then you are having psi bar gamma mu psi. Okay, now if you see, this is not invariant. You are having the Lagrangian here, okay, and an external term. So L prime is equal to L plus this q, so partial mu theta of x, this psi bar psi. So gamma mu psi. Okay, so let's call this as equation first. Now if you see under this local phase transformation, my Lagrangian is not invariant, or in other words, the action for the Dirac field is not invariant quantity. Clear? The free Lagrangian. Now what I will do, I will introduce a term to make this Lagrangian invariant. Okay. So what is the external term? Let's say, okay, so let's say if this theta is independent of x, then the differentiation of this is 0 and our Lagrangian is invariant. Clear? Okay, so now, so what I will do, I will introduce a kind of another field so that this Lagrangian becomes what? Invariant quantity. So in other, okay, so what I will do, okay, so I will write, so introduce some field, because Lagrangian is an additive function. Okay, Hamiltonian is an additive function. Is that true? Lagrangian function and the Hamiltonian function both are additive. You can add and subtract terms to these functions. Clear? So that's why I will introduce an arbitrary term in that way in our original Lagrangian to make this, okay, to remove this very term here, or in other words, to make our Lagrangian to be invariant under this kind of transformation. Samajh aa? And then we will interpret what exactly that term means. Okay, so let's say introduce some auxiliary field. Okay, let's call that field as some a mu, such that our Lagrangian L is invariant under local U. Okay, so what does it mean? So it means I am taking this psi bar I partial slash minus m psi. So I will take it like this thing, minus q some a mu, okay, psi bar gamma mu psi. So this very term, and here I will introduce a field A. Samajh aa? Got it? So what I have introduced is an additional term, this very term, and we don't know what exactly this term means. Samajh, we don't know what is the interpretation of this A. So it is some auxiliary field we want to introduce in such a way that this term is removed from here. Got it? Okay. So what I will do, okay, so now let's take now the transformation again. Under this transformation, under psi goes to psi prime is equal to e raised power minus I q theta of x psi. So when I make a transformation of my field psi to psi prime, so I will assume we are having a transformation on this A as well. Okay, in a transformer frame. So let A mu go to A prime mu. We need to figure out what their transformation is. Samajh aa? Okay, so what I will do, so therefore this L goes to some L prime. What is that? L. So this very object goes under transformation as equation 1. So L plus Q partial mu theta of x psi bar gamma mu psi. This is the transformation rule for what? This L under this very transformation, and I am having this very term minus I Q, sorry, not I. So minus Q. So this will transform as A prime mu psi bar gamma mu psi, because this is a field. Samajh aa? Now what I want to do? I want this term cancel this term. So it means I am having L plus some. Let's take Q out. So I am having some partial mu theta of x minus A prime mu, okay, psi bar gamma mu psi. Call this as equation 7. Okay? Samajh aa? Everybody? Now if my, okay, so what is our original Lagrangian? So this is now our original Lagrangian, is it? This total term we want to be invariant. That means out of this thing, I should get this back. Samajh aa? So I can take this minus out. Let's take this as plus. So make this as a minus. Can I take? Now, Okay, so if what I need to figure out, transformation rule for A, is it? So what I am saying, if A mu goes to some A prime V, which I don't know, let's write it in terms of A mu plus some partial mu theta of x. समझ आया? You got it? So what does it mean? Then this A prime minus partial, it is simply A mu. Okay, so this object is simply there. So in this case, so this will be simply therefore as A mu. So what I am getting? So which implies therefore L goes to some L prime. So that's equal to L minus Q A mu. Okay, psi bar gamma mu psi. What we have got? We have returned our Lagrangian. Huh? So that means in order for our Dirac field to be invariant under this local phase transformation, we have introduced a term like this thing, such that this total object is invariant under a transformation. Okay, if and only if this holds. So if this transformation holds. Got it? So why from this theta comes? It's actually the angle, or it is actually the phase. It is here. It is this very phase. Where this phase arises, it is actually the parameter of the group U1. So because this is a U1 group, the set of all elements formed by this exponential, okay, forms a U1 group, and this theta will be a parameter for that very group. So you got it? Okay, so that means this transformation is induced by a U1. Or in other words, this transformation is induced by a local U1 group transformation. So that means if you now identify, this is simply the gauge transformation of the second kind in electrodynamics. Correct? So why the potential is transformed this way, and it has now the origin where? In a group theory. Do you identify it with something? Do you identify? Have you ever seen this kind of equation? Where? In electrodynamics. So if this A is actually the vector potential, or if A is the electromagnetic field, or A represents both phi and A, okay, the 4 vector, then this is simply the gauge transformation in the electrodynamics for the electromagnetic field. Clear? So what we have identified, okay, now this transformation has its origins where? In a local U1 gauge group. So we call that as, okay, so this very set set of all these elements, so you can call it as a local U1 group, or in other words, it is something, we call it as a gauge group. So in other words, okay, so we can identify this A to be the EM field. So now we are having EM field as a gauge field. Okay? Okay? So now the point, okay, so let's summarize what we have done. Okay? So let me summarize what we have done. Okay, so in order for, okay, so we started with a global U1 symmetry, or we started with a global phase rotation, and we saw our free fields are invariant under this very transformation. Now what we have done next, we have made this global transform as a local U1 transformation, or local phase rotation. Under this local phase transform, free fields do not transform, okay, do not remain invariant, or the free Lagrangians do not remain invariant. Clear? So to make a given Lagrangian invariant, we have invented a term, or we have introduced a term which fixed this invariance. Clear? Got it? And we identified that term with a gauge field. And this procedure of reducing a global symmetry to a local symmetry is called as a gauge fixing, and the hypothesis is known as gauge principle. Got it? So reducing a larger symmetry to a smaller symmetry, or fixing a global symmetry with a local symmetry, defined as a gauge principle. Got it? And as a consequence of that, there emerges a field, what we call as a gauge field. Okay, here in this very case, in this very simplest of the examples, while we are having only the U1 symmetry, which is gauged to a local U1, we got actually a EM field as a gauge symmetry. In other words, I can say the electrodynamics, what we know, okay, is a gauge theory, okay, with a gauge group of U1. Got it? Clear? So now if I am having an additional symmetry, let's say if we enlarge this very symmetry, and let's take this theta, let's take something, this kind of object. Psi goes to some psi prime is equal to e raised to power minus I. Let me write some q, okay, Ta theta a. Where Ta are the generators of a given Lie group. Samajh? Let's take SU2. How many generators are there? 3 generators. Okay? So think in terms of the Pauli spin matrices. Clear? So then, okay, so we'll be having a, instead of having this A mu here, I'll be having another kind of gauge field. Samajh? So a gauge field which will respect the symmetry under this kind of transformation. So that is known as the Yang-Mills field. Okay, so that defines your quantum chromodynamics, or simply let's say that defines your electroweak theory. Clear? Okay, but we will not go to this theory. We will be only restricting ourselves to this thing. Okay, so now what we have at hand. So let's write now since we have identified this with the electromagnetic field. So I should introduce now. So this term is actually the free Dirac field. This is actually the interaction between the electromagnetic field and the Dirac field. It is an interaction term now, and I need to introduce what? The free field for the electromagnetic case. Clear? So what will be that? So our Lagrangian. So let me write now what we call the Sipner quantum electrodynamics. Okay. So our Lagrangian for Sipner quantum electrodynamics. Sipner means so we are dealing with the electrons, fermions, spin half particles at least. So it is L is equal to, so this is now the Dirac field psi, and there is an interaction Q. Let's say you are having E mu psi bar gamma mu psi, and so this is an interaction. So this is your fermion. Okay, so this is the interaction, and there will be now the gauge field itself. So it is F mu. Okay, so this is your EM field. Samajh? Got it? So this represents our signal requirements. Okay, so now let's go to the Feynman rules. If you have any question, just tell me. Then we will take, so this term you can also write as minus Q, okay, J mu A mu, where J mu is this vector. Okay, and Q is the charge carried by a fermion. Let's take only the electron. What will be the charge? Minus E. So if E is the some charge, positive unit, so you are having 1 unit of charge on the electron, okay, but with a negative sign. So then Q will be minus C. Any question till now? So let's take the Feynman rules. So for QED. So the first thing is, so if you are having a propagator now, a photon propagator in a given diagram, so what it means, so you are having, this is one vertex, since the propagator is a line between two vertices, clear? So internal line between two vertices. So we show that by a wavy line. A wavy line represents the photon propagator. Clear? So this is our propagator. How we write it? As d mu nu sum x minus x prime. So if it is some x and it is x prime, so it is represented by what? D mu nu. समझ आओ? Okay, so there is no, I mean, the arrow on this thing. So the arrow will be fixed by the arrows of the fermions. Okay, the way we have done it in the Yukawa interaction. Clear? Okay. So another thing is, so you are having, let's say, if this is, now tell me, the photon line is shown by a wavy line. Now can anybody tell me what this line is? Is this an incoming line or an outgoing line in a diagram? It's an incoming line because it goes into the vertex from the left. So this is our incoming photon field. So for that we'll write some epsilon mu of k. So we'll put a factor because it comes with a polarization. So for fermions it comes with those signals u and v. For scalars there is no function. Clear? For photons, since it carries a polarization which describes the photon itself, so we call that as this epsilon mu. So now tell me, what about this thing? So this is an outgoing photon. So we'll write this as some. So sorry, this is with the epsilon star and this is with the epsilon. Okay. Now what about? Okay. So what about this thing? The interaction. Okay, let's say this is some vertex is there. So how will we write interaction? So what is our Lagrangian? So Lagrangian minus QA mu, okay, psi bar gamma mu psi. So then you will understand what this mu, where I will put this mu and nu. Samajh aaya? Okay, so let's write. So how I put the interaction? Let's say how I identify with the vertex. Vertex means what? You remove all the fields, whatever the functions there remain. So that defines vertex, the interaction strength. Clear? So if you remember, if you are having the Yukawa interaction, what was there? So it was minus g psi bar psi phi. Okay, and you call the vertex, let's say the vertex, this kind of vertex. Okay, so what is the factor you put for the vertex? Okay, so you strip this strip of the Lagrangian with the fields, and whatever is remaining you put that as a vertex factor. Clear? So what is the vertex factor? So it is g, so you put as minus I. Clear? So what is here? So what is the field? A is the field, psi bar is the field, psi is the field. Clear? What remains there? So you remove all the fields. What remains there? Q and gamma mu. So forget about this minus because I have to. This is an interaction Lagrangian. You have to make it as an interaction Hamiltonian. Then this minus will be gone. Okay. So the vertex in the QED, let's say you are having some photon, some fermion, whatsoever. Okay, some fermion. Okay. Let's say so this means the rest of the diagram. Okay. So the vertex in the QED, so this is the rest of the diagram. Okay. So this vertex will be represented by, can you tell me now? Minus I, Q and gamma mu. So now if you see, the vertex has actually the vector nature. So QED, actually the electrodynamics is a vector theory. So it is actually, look at this, the interaction Lagrangian. So it's a vector interacting with the vector. This psi bar gamma mu psi transforms as a vector under what? Lorentz transformations. Is it? Tisha? And A mu is also a 4 vector. Clear? Under Lorentz transform. This is a vector interacting with the vector. So A mu is a vector, you can say, and this is actually the current, 4 current, so generated by the charges and the currents itself. Moving charges. Got it? So then the nature of the interaction is actually the vector interaction in QED. Got it? That's why this vertex has to be a vector. Now if I am having, let's say this is one vertex and this is what? Another vertex. So for this vertex I will write, let's say minus I q gamma mu. So for this vertex let me write another gamma mu. So that means you are having mu for this vertex, mu for, and in between is what? D mu nu. So samajh aaya? so that this entire object is a scalar quantity. It's like this thing. So you write it as something g mu nu. So mu gets contracted with this mu, nu gets contracted with this mu. Samajh aaya? Got it? So this is how we put the rules. Clear? Any problem? Okay. So let's go to the final diagrams at the lowest level. Oh, sorry. This was correct for the incoming. So you are saying for the outgoing is the star. Okay. Let's look at QED at a single vertex. Only one vertex is there. Then we'll move to the QED at two vertices. Okay. So what is our interaction Lagrangian? Okay. So what does that mean? So what? Okay. So let's look at the S matrix again. So this is our S matrix 1 minus I integral d4 of x hi of x. Is that true? Then what you are having minus 1 by 2. Then d4 of x1, d4 of x2, then time order hi of x1 and hi of x2. We'll be dealing only till this video, like this. Samajh aaya? So let's look at the Lagrangian. Let's look at the first term. So we'll evaluate. So what is our interaction Lagrangian? So it's minus q a mu psi bar gamma mu psi. Clear? Okay, so now let's decompose this A. So what will be, okay, so tell me what is the interaction Hamiltonian? Anybody? So the interaction Hamiltonian will be simply plus of this thing. So let me write the normal ordered interaction Hamiltonian. It's A mu psi bar gamma mu psi. Why? Because when you take from P, okay, L to H, so if there are derivatives, then you have to look at. When there are no derivatives, it will be PQ dot minus L. Samajh? So minus and minus will be what? Plus, since there are no derivatives, the first PQ dot, those terms will be 0. Samajh? What if that's why you have to change? Let's say if it was something partial mu A nu, some derivative of this thing or the derivative of this thing. So what you have to then do? You are supposed to figure out what is first conjugate momentum P, then take PQ dot those terms minus L. Samajh aaya? Got it? So but since there are no derivatives, PQ dot terms will not contribute. Only what? Minus L. So minus and minus will be plus. Okay. So let's look at this thing. So I will decompose this A mu as, so A mu plus A mu minus. So what it means? So A mu plus means the annihilation of a photon. A mu minus means, so this means what? Annihilation, and this means creation. So the way we did in the Yukawa theory. Now again, what is our psi? I will put a psi plus and psi minus, and then psi bar I can put a psi bar plus psi bar minus. Can anyone tell me what is psi plus? Psi plus is actually the annihilation operator for a fermion. Psi minus will be creation operator for an antifermion, and psi bar plus will be annihilation of the antifermion, and psi bar minus will be the creation of a fermion. Got it? Okay. So now let's try it. So let's write this interaction Hamiltonian. So normal ordered one. So because interaction Hamiltonian, this hi of x, it occurs at what? The first order. Samajh 1 minus integral d4. We need to only then integrate it over d4. Samajh? So for the time being, I will forget about the integration over d4. I will take only this thing to look at what kind of diagrams are possible or what kind of processes are possible at one loop. Samajh? Okay, so now let's calculate it. So it is Q. Okay. So what it is? Just tell me how many terms are there. So let's write A mu. So it is A plus mu psi, sorry, plus A, A minus mu, okay, then you are having psi bar plus psi bar minus, then you are having gamma mu, then you are having psi plus psi minus. Clear? So let's expand it. How many terms are there? 8 terms. Huh? So I'll put like this thing. So this means all the terms are, I'll keep this normal order outside. Huh? So sure? Otherwise every term I have to put the normal ordering operator. So it will be something A plus mu psi bar plus, then you are having gamma mu psi bar. Clear? Like this thing. Then you are having A bar plus mu. Okay, what I have written. Then you are having this psi bar plus gamma mu psi. Okay? समझ आया? Plus rest of it. So those you need to write yourself. Okay? So I will draw only the diagrams of all the possible terms. Now tell me. Okay? So let's look at this everything. So all these happen at a single point, is it? So what is the argument here? X. So that means this is A mu of x, psi of x, psi of x. Clear? So all these processes happen where? At a given point x. So now let's draw the diagram. So what is A plus? So let me put the first term. So this is the vertex. Clear? So first we will draw the vertex. So what is A plus mu? It means the annihilation of a photon. Clear? So where from the annihilation comes? Annihilation line comes from left to the right. That means the line goes into the vertex. So let's write this is the annihilation of the photon. Is this the annihilation of the photon? समझ आओ? Now tell me what is psi bar plus? Psi bar plus is annihilation of an antifermion. That means annihilation is again where? So it's the line coming from left to right. So let's write. So this is the annihilation of what? Antifermion. Okay, because antifermions carry the opposite sign. Eh? So it means it's a antifermion going into the vertex. Now then what is psi plus? Annihilation of a fermion. Is that true? Yes, sir. So where is the annihilation? So a line coming to the vertex. So this is our term. This A plus mu psi bar plus gamma mu psi. And what is the vertex? Okay, so you are having here Q. So let's put it as a normal order. Okay, what this is minus I Q gamma mu. So this is the vertex. Now look here. There is no outgoing line. Clear? So it means everything is in the initial state. In the initial state. So all the lines. So you are having a photon. So it means okay. So let's interpret this very diagram. It means you are having only the initial states, no final state. So this is one of the interpretations. And the second interpretation is that you annihilate a photon. When you annihilate a photon of given energy, what you create? There is a pair production. Clear? So this is a fermion and this is an antifermion. It's simply a pair production. Clear? But once you, let's say, if in the normal routine when you annihilate a photon, it is an initial state. So you create what? Fermion, antifermion. Where they will go? To the final state. But where they are going here? In the initial state. So that means all these particles are where? In the initial state. You are creating an antifermion pair, okay, out of a annihilation of the photon. Okay, so they tend to be where? In the initial states, and this is not possible. So when you create something, it should go to where? To a final state. So that means this diagram is not possible. So this process is not possible. Not a physical process. Okay? So let's draw all the possible diagrams. So let me draw. Then we'll see what's happening. Okay. So I'll be having this kind of diagram. So an initial photon. So this is the process psi bar minus gamma mu psi plus A plus mu. So it is this very term, just check. Okay, then you are having its conjugate process. So like this thing, then you are having psi bar plus gamma mu psi minus A plus mu. So, okay, so then you are having like this thing. Okay. So this is our vortex. Okay. So then you are having this kind of diagram. Okay. Then you are having this diagram. The same thing, but the photon is in the final state. So you are having psi bar minus gamma mu psi plus A minus mu. Then you are having this kind of diagram. Psi bar plus gamma mu, like this thing. Then you are having the last diagram opposite to this. So that is something. Okay, now you can check. These are all the possible diagrams. A diagrams are here. Clear? Okay. So now let's check whether these are possible or not. So what we are trying to look, we are looking at whether. So we have only considered an electron interacting with what? A photon field, without presence of any other external field. Let's say you can be having a possibility an electron is coming nearby the nucleus. Or a photon is coming by a nucleus, a heavy object. Those things we are not considering here. We are only simply considering you are having some electron, okay, and it's interacting with an electromagnetic field created by something else. So let's say you are having a Coulomb potential that creates an electromagnetic field, let's say static electromagnetic field, and electron is interacting with that very Coulomb field. You are having an electron-electron interaction. Okay, so we are looking at those kind of things. We are not considering a photon coming by a heavy nucleus. So let's consider whether these processes are same. So what? So let's look at the momentum conservation of this very process. Momentum conservation. Let's say if you are having P is the momentum of 4 momentum of electron. Let's say, and P prime is the 4 momentum of, let's say, positron. I will take fermion and antifermion to be electron positron, and let's say K is what? 4 momentum of photon. Clear? So what is the conservation of momentum in all the diagrams? So it will be the possible combination of this thing. Somewhere it will be P is equal to P prime plus K. Somewhere it will be what? P is equal to K minus P prime or something like that. All these combinations, linear combination. What I mean by that? So you check in all the diagrams what could be the possible rule, conservation. So let me write it in this way. A conservation rule will be in all the diagrams. So 4 momentum conservation. So at a given, because at a given vertex the conservation rule must satisfy, is it? So the momentum conservation should be at a given vertex. So it will be like this thing. Let me take P is equal to plus minus P prime plus minus some K, because these are all the possibilities. Is that true? So all the possibilities are included here. So now let's square it. So which implies P square is equal to plus minus P prime plus minus K whole square. So what is that equal to? So it is simply P prime square, because all the minus will make square. So it will be something K square. It will be plus minus twice p prime dot k. Clear? समझ आया? Okay. So what it means, since these are all the external lines. समझ आया? There is no internal line in the diagram because you are having only one vertex. All are the external lines. What they are? They are the real particles, or we call them as the on-shell particles. Okay, since all particles are on-shell. What does that mean? So it means this p square must be equal to m square. M square is the mass. Okay, since I am having electron and positron carrying the same mass, so I will write similarly p prime square equal to m square. What for the photon? So since photon is the massless, it should be equal to 0. Clear? Okay. Okay. So now let's look at that very diagram, that very thing. So it is m square is equal to m square plus 0 plus minus twice p prime dot k. So what it gives me? So it is p prime k dot equal to 0. So this is a law, since this is what? A dot product between four vectors. So in other words, it's like this thing. P prime mu, k mu, that's equal to 0. And this is what? A Lorentz invariant quantity. Is it true? Is this invariant under Lorentz transformations? Because it is a scalar product, four scalar product, it's a invariant quantity under Lorentz transformation. When something is invariant under Lorentz transformation, that means I can choose any frame. So let's choose a frame of reference. So we can now choose any frame of reference. Any frame of reference. Why? Because since this product is a Lorentz invariant quantity, or this dot product is Lorentz invariant quantity, it means it's independent of frame of reference. So that means I can make calculation in a simpler frame. So that will be valid for any arbitrary frame. Okay. So let's do that. So let's take any arbitrary frame. So in which, let's say one particle is at rest. In which one particle is at rest. What does that mean? So I will choose a frame of reference where this p prime is simply equal to m 0 0 0. समझ आया? So let's say one of the particles is where? At rest. Got it? समझ आया? So now what this condition demands me? So I need to look at, so this condition should satisfy in this frame of reference. समझ आया? When I am saying this is independent of frame of reference, so it should be satisfied where? Here. So what is our k mu? K mu is the force momentum of the photon. Okay. So I am having this k mu. So it is something, energy of the photon, let's call that as omega, and the momentum corresponding to photon. Clear? So now let's look for that very condition. First tell me. So if I am having p prime dot k, so what that will be? M. Okay, so it will be m omega plus 0. So that has to be equal to, what it means then? So omega has to be 0. So in other words, in this frame of reference, so in this frame, photon has to be space-like. Space-like. What does that mean? So I will write k mu for the photon is equal to 0 and now if you take the dot product between the two, so that condition is satisfied. So much on? Everybody is following it? Clear. So now let's take, now that very condition is satisfied, p prime. Okay. So now I am saying p prime dot k equal to is satisfied. Okay. So now let's look at this k mu. So I will take this k mu, it's k mu, so that's k square. So much on? So let's take what that will give me. So it is 0k and dotted with 0 minus. So what is that equal to? Minus k square. What that is equal to? 0. By definition, k square is equal to 0. Okay. So this object is equal to 0. So much on? So what it means? K square equal to 0 implies the momentum is equal to So you don't have the energy component here. Now what it implies? Momentum has to be 0. So that means photon does not exist. Huh? So it implies photon does not exist. Okay? So when photon doesn't, that means this process does not exist. So in other words, the single vertex QED does not exist. Okay? As a bare single vertex QED does not exist. Or in other words, there are no process at the single vertex. Now there can be the process at single vertex. Let me tell you how. So let's say you are having a heavy nucleus and a highly energetic photon comes. It interacts with the nucleus and there is a pair production. So this photon has actually interacted with some additional source which made it to have the pair production. Samajh? Got it? So we have not considered those kind of process. Okay, so that's in presence of the external field. We have not considered those kind of situations here. This is something what we call it bare. I mean as itself, bare objects. Clear? Got it? Any problem? Any problem? Now let's look at the QED at the second, order. Second, okay, next vertex. Okay, so this is possibility that these diagrams can be inside a bigger diagram. Then it's not actually a single vertex QED. It is what? Then a many vertex QED. Let's say you will be having a diagram. Let's assume like this thing. Let's take this kind of diagram. Okay, so if you see, let's bisect this very diagram like this thing. So you are having this vertex. You are having this vertex. Is that true? Samajha? So these are actually the vertices of a bigger diagram. This. Okay? So this is a second order diagram. Huh? But this is a separate kind of thing. Huh? Okay. Let's see. Second order QED process. Okay, so what I need to look. So what is our, so in the second order, if you look, there is a time ordered product of this HI of x1, HI of x2. Clear? There is a time ordered product. Now let's apply, okay, what is our HI? So there is a time ordered product of, what is our HI? So Q, so let's, okay, Q psi bar of x1 gamma mu psi of x1, clear? And there is an A mu. So let's write it here. So this is the one, and then you are having again Q. So this very object, then you are having this Q psi bar of x2, okay, gamma mu psi of x2 A mu, because mu is a domain index. Clear? Isha, am I going fast? Huh? Okay. So now what I have to do? When you are having a time ordered product, you apply Wick's theorem. Wick's theorem says you first normal order everything. The first term will be what? So apply Wick's theorem. So I may take few minutes more. Apply Wick's theorem. Wick's theorem says first term will be normal ordering of all the terms. So it means, so you are having Q square, Q psi bar of x1, so normal order, gamma mu psi of x1 A mu, then you are having, okay, so let me write it. Okay, then you are having psi bar x2 gamma mu psi of x2. What is the next term in the Wick's theorem? So all the single contractions. Then you have to contract the fields, is it? Samashama? But singly, one pair. So this is Q square, it will come out every time. So let me write Q square here. Okay. So what is the next term? So you write it again, psi of x1, gamma mu, then contract the fields. Okay. Gamma mu psi of x2 A mu. Okay. So what is the possible contraction? you can contract with, let's say, A. समझ आवा? Now let's take another single contraction. What is the another single contraction? Huh? So plus, so let me write it. So you are having the psi bar x1 gamma mu psi of x1 a mu. So this is the first term at x1. Then you are having psi bar x2 gamma mu psi of x2 a. Okay. So let's contract it. You can contract, let's say, this psi and psi bar. Can you contract it? Huh? A mu I have contracted. Now the another single contraction plus another single contraction psi bar x1 gamma mu psi of x1 a mu, okay, psi bar x2 gamma mu psi of x2 a mu. Okay, so you can contract, let's say, this psi and this psi bar psi. समझ आवा? Plus other single contraction. So I will not write those as a single contraction. So these are the single contractions. Now what you are having? Plus double contractions. You contracted, you are having two contractions now at hand. So what that is? Psi bar x1, okay, then you are having this gamma mu, okay, psi of x1 a mu, clear? So what you are having then you are having this psi bar x2 gamma nu psi of x2 a nu, okay. So you are having two let's say A is contracted and let's say this psi and this psi bar is contracted plus all double contractions. So I will not write, you have to do those. समझ आया? So I will just draw the diagrams in a moment. Plus then you are having all the three contractions. Let's say, since how many fields are there? 6 fields. So that you can make 3 contractions. समझ आया? Got it? So all the fields will be now included. So you are having now psi bar of x1 gamma mu psi of x1 e mu. Okay. So you have to take care of actually. I mean the same types of field should be contracted. Fermion will contract with the fermion's field and photon field will contract with the photon field. So you can have the contraction with this thing, contraction this psi with psi bar, and the contraction with this psi and psi bar. समझ आया? So that means all the possible 3 contractions. Now let's draw the diagrams. We are almost done. There is no problem. Let's draw the diagram. Okay. So first is actually the normal ordered product. It means in this very term all annihilation operators are on the left of the creation operator. So this will give us nothing. Okay. So this is simply the 0. When you take a given process, this will be 0 in that process. Now let's take this thing. So what are the fields remaining? Now tell me which field is contracted. So this is at x1. This is at x2. So A is multiplied with x, x1, x2. Okay, just right. So this is actually where? This is at x1 and this is at x2. So this is at x1 and this is at x2 and so on. Okay. So now let's look at this very term. So what kind of thing? Which is contract? So you have to draw first 2 points. So which will simply give you what? Vertexes. So you are having one vertex at where? At x1, another vertex at x2. Which field is contracted? A. So when you are having a contraction of A fields, it gives you a propagator. So that means you are having between x1 and x2 a wavy line. So this is the contraction. So A mu contraction. That's your propagator. G mu nu of x1, x2. So this is your x1 and this is your x2. Got it? So now what you are having at x1 there are actually, so this represents annihilation and creation of what? Sorry, annihilation of the photons. Sorry, annihilation of the fermions. So that means in the initial state you will be having like this thing. So I will not draw the arrows on this thing. That means in the initial state you are having fermions and antifermions, and in the final state you are again having what? Because there is nothing contraction on the fermion field. So it will be like this. समझ आओ? So it is simply, if you see, this diagram represents, let's say, electron scattering, electron positron scattering. Okay, so all the possible fermion or fermion antifermion scatterings. समझ आओ? So it will depend upon which process you are choosing. Then this psi bar will be something psi bar plus, and this will be psi minus, and so on. The way we are doing. But I am not interested in here, so I'll be only interested in what kind of diagram I am having. So this is simply a two particle scattering, if you see. So you in the initial state you can be having electrons and electrons, muons and muons, and so on. And the final state you can be having the same thing. Okay, or you can be having electron positron in the initial state and the electron positron in the final state again. So got it? Okay. So now let's look at the next term. Okay. So where you are having this. Okay. So let's look at this very term. Okay. So which is contracted? Tell me. So you are having point this thing, and then you are having this very point. What is contracted? Psi is contracted. That means I am having between points x1 and x2 a Dirac propagator. Because when you are having psi, okay, so this is your psi bar or psi bar psi bar contraction. So this is simply our word Dirac propagator. Okay. So what you are having in the initial state at x1. So this is the point x1, and you are having this as the point x2. What are the fields at x1? You are having a fermion field and a photon field. So it's like this thing. So let's say you are having a fermion field, or it can be fermion or anti-fermion, because psi bar contains both fermion as well as anti-fermion. Then you are having actually a mu, that's photon field. So you are having like this thing, and you are having again a photon field at point x2. Now if you see this, actually let's take this fermion only as the electron. This is actually the scattering between electron and a photon. What is that scattering known as? Compton scattering. So that means this diagram represents your Compton scattering. Got it? Electron photon scattering. So now the Compton scattering is actually a second order process. The lowest order process Compton scattering arises in QED is the second order. Got it? Okay? So you have to. So there are actually two diagrams. I will tell you in a moment. Okay, how they are actually two. Since this is actually the photon here at this very point, you can think this diagram as an electron going in space. Okay, so then it loses some energy. So when it loses energy, so you will be having what? A photon. So then it again goes, it loses again the energy. So two photons are. It may happen. So the electron goes in the space and absorbs a photon, and it goes and releases a photon. So you can be having another kind of process like this thing. So an electron goes like this thing. So let me write it like this thing. So electron goes in space like this thing, and you are having this electron line, it moves. So it may happen. So in the final state, it absorbs an electron, or it absorbs here. It radiates and they absorbs in the initial and the final states. So is this also the electron photon scattering? Is this a scattering? So in this diagram you can write like this thing. So you can have equivalent diagrams of like an electron goes and it may go. So this is, let's say, electron. So these are the initial state electrons. Okay. So there is an exchange of what? A photon. Clear? So it may also happen the external, these final states may exchange. Let's say electron goes, two electron goes with the momentum P1 and P2, and it may retain the same momentum, the elastic scattering. It may also happen they will exchange the momentum. So much like this thing. So you can be having like this kind of process. So electron going. So these are the initial states. It may happen they may change what? Momentum in the final state. So scattering can happen. So the momentum remains unchanged. They retain the same momentum, or it may happen what? They interchange the momentum. Clear? So these are equal. So this diagram represents everything. Here. So this is actually a symbolic diagram, but when you have to do the calculations, these are the diagrams which will contribute to electron-electron scattering. And when you do the Compton effect, this is a symbolic diagram, but when you do the computations, it will be actually this diagram plus this diagram. So, got it? Okay. So now let's look at another diagrams where you are having two fields getting contracted. You are having psi and what? Photon. So let me write it this way. Instead of psi, two A's, so let me do it this way. Let me contract it here, this psi bar with this psi. Okay, so let me take this very diagram because that has a physical mean. So let's look at this very diagram. So you are having a point x1 and x2, which is contracted. Two sides are contracted. Clear? So that means you are having a one contraction and another contraction. What is remaining? Is. So you are having a photon field here and photon field here. So let's say, clear? So it gives you what? A pair production at this very point and a pair annihilation at this very point. So these are loop diagrams. So they give actually the contribution to what we call a Lamb shift. Or they contribute? Not. They contribute to the Kashmir effect. Okay, so you can explain Kashmir effect based on that very diagram. Okay, so now let's look at the last diagram. This way, you will be having another possible diagrams as well. Let's look at this very term. So this is this very diagram. Now let me look at this very diagram. Okay. So let's look at the last term. So what is last term? So everything gets contracted. Okay. So you are having the fermion field, then you are having a photon field, and you are having like this. Okay. So we call these as a bubble diagrams. Or they contribute to the vacuum polarization. Okay. So this is also a vacuum polarization diagram. This is also a vacuum polarization. They got it? So these are all the process happening at lowest order QED. Okay. So we'll be doing another process. What we call it. We'll do only one process because we are running out of time. So we'll be doing let's say only the Rutherford scattering. Okay. So using the rules of QED. Got it?